Hello everyone, I am Haris and I am pleased to present my paper at this conference. I am the first author and this paper has been written with Vibhu, Gautam, Richard Hawkins, Rob Alexander and Ibrahim Habli from Department of Computer Science, University of York. And this research work has received funding from the European Union's Horizon H 2022 Research and Innovation Program. So first I will talk about the motivation of our work. Healthcare resources are very scarce and artificial intelligence solutions are being deployed to reduce the burdens of the hospitals. Conversational agents have been used and are currently being deployed because they provide interactive and natural language of communication which humans can understand. A few examples of conversational agents are Google Assistant and Amazon Alexa, and the conversational agents can also run in the smartphones and can also be accessed through web interfaces. In order to deploy in healthcare, they need to be robust and safe, so that the patient safety is assured because they use machine learning algorithms. Machine learning, especially deep learning models, are applied heavily in research, and they suffer from uncertainty problem on unseen data, and in the classification models they tend to provide incorrect classification when they see unseen data, and also they provide high confidence, which is a softmax score. The model does not provide any certainty measure when they predict any class. In safety critical systems, it is very important that we know if the model is not certain, so we can devise any safe decision making strategy to overcome to reduce the harm to patients. And in healthcare, this will especially in diagnostic decision making, this could be very helpful. So here I will just present a typical architecture of conversational agent. Conversational agent usually utilize sequential architecture with understanding, which is implemented through natural language understanding module and decision making, and a response generation module, and they work in sequence to complete a task. And if the conversational agent is voice based, so we can also add one more component at the start, which is the automatic speech recognition. So in understanding the task which is usually implemented, is intent classification and slot filling. So as an example, if I need to book an appointment at 3 p.m. on Friday, so the intent would be book an appointment, and the slots are the values that are needed to complete that task. So in this case they are 3 a.m. and day is Friday. The decision making module takes a decision after understanding, and then generates a dialogue act. A dialogue act is just a composition of intent and the slots, and then response generation converts the dialogue act to human readable form, which is like a text utterance. And if there is if the conversation agent is voice based, so there is a module which convert text to speech, and then the user can hear the response. In this work, our main contributions are utilizing Bayesian LSTM with Monte Carlo dropout to measure this uncertainty in the intent classification for conversational agents. We also present a use case which shows our method and how it can be utilized in healthcare domain. And also we provide an evaluation by using an out of distribution data set, and then we compare the results with in distribution data. So this is the use case that we have, On the right side, this is, as you can see, the schematic diagram of our use case. So hospital utilizing conversational agents so they can reduce the calls that hospital staff has to take. The patient can interact with the conversational agent, and the conversational agent's role is to and they provide their health condition. The conversational agent will understand the request made by the user, and based on the intent they can classify if the user needs certain kind of doctor, and then before taking any decision, if the system is not certain, we can apply any safety strategy. Here we use an entropy value, which I will discuss later during this talk. So the method we have applied during our work is the Bayesian approach, which allows us to provide a certainty measure. So we compute the uncertainty that the model has in a prediction by applying dropouts at runtime in the deep learning model. So instead of a point-based estimate, which is probability score called softmax in deep learning, we use here Bayesian approach that provides a probability distribution. So we have a distribution of softmax values which we can average, and we can compute the uncertainty by using Shannon's entropy method. So this provides increased confidence in decision making, and also it provides a measure of how much the model is uncertain in the prediction. In order to apply this use case, we used an open source healthcare dataset for intent classification, and there are 6,661 utterances containing 25 unique intents, which, as you can see on the right side in the chart, the intents distribution is they are not imbalanced. There is an almost equal number of amounts of intents in this data set. For example, there is an utterance that I cut my head a couple of weeks ago in hand, and even though I keep using an antibiotic cream, it's not getting better. And the ground truth, which is the intent we want to identify from the patient's utterance, is infected wound. For our model, we used an 85-15 split. So the training size was 5,661 utterances, and testing size was 1,000 utterances. So this is the architecture of our model. On the right side you can see the output shape and number of parameters. We use for our recurrent neural network architecture LSTM cells because they provide for sequence classification. They are heavily used in conversational agents for intent classification tasks, and they also are better than vanilla RNN networks. So the word embeddings we learned with the model. MC LSTM is our LSTM layer where we sample hundreds of max values. Basically we run the model 100 times, and we get multiple we get a distribution of softmax values. And in this layer we used a random dropout, which is at test time of 0.7 to compute the model uncertainty. So normally we use dropouts during training time for regularization, but in order to compute we are using it at test time. So here I present the model performance. So as you can see on the left side, there is for each of the intents. There are some intents missing because the table was too big. The model's accuracy was very good on the testing data set. It was 99.4, and also the model performed well in terms of recall, precision, and F1 score. So they are almost 99.4, and as you can see on the you can see also on the right side of the chart in the confusion matrix that there are very few predictions that the model performed incorrectly on the testing data set. So it means our model is very almost perfect, and it is not and the recall and F1 score also means that it is not generalized to just training set, and the performance is very good on the testing set. So here are the results of the uncertainty that we computed on our data set. So on the left side there are the tables, and I will start talking about the in-domain utterances. So these are the utterances that the model has seen during its training. So I randomly picked some examples to show you the entropy, and this is the entropy that is measured by running the same network 100 times. As you can see, the predictions so the predictions for each of them was right, and this is due to the model has a very good performance, and the entropy values are very small. So it means that the model was certain that it has seen those examples. And if on the bottom side there is a test utterances, so for the test utterances which are from out of distribution, so the out of distribution means that these examples the model didn't see during its training. So this is a totally different data set that we use, which is used to evaluate any model for text data on out of distribution for out of distribution evaluation. So as you can see, am I connected to Wi-Fi and some other things, some other examples. So the model still predicted, because it's a classification model, so model predicted feeling cold, which is a totally incorrect prediction, but with the help of entropy, because as you can see the entropy values are very high, so it means the model is very uncertain about these examples. In total we had 1000 examples, and on the right side you can see the charts for the entropy calculations. So on the top one is the sample data, which is 1000 examples randomly selected from the in distribution data set, and the mean entropy was very low, which is shown by this red dotted line. And apart from only one sample out of 1000, the entropy was not high. So it means we can the model the entropy, which was our initial hypothesis that we can provide an certainty score, is correct. And if you see the other chart, which is the out of distribution samples, so out of distribution samples are also 1000, and the entropy values are very high. So the mean values is around 2.0, and generally they are very high than the in distribution entropy values. So this basically confirms our initial hypothesis that we can use this Bayesian approach for measuring uncertainty, and then this uncertainty estimation can be used for safe decision making. So in conclusion, we successfully demonstrated robustness of our LSTM model, which was performing intent classification tasks using this Bayesian approach. So the model is robust on out of distribution data set, and it could, apart from one or two examples, out of 1000 samples, it could measure the entropy value correctly. So in comparison, as we see in the last slides, the entropy values are much higher for out of distribution data, and from the results, this score is a reliable measure. So this entropy score can be used in different ways. In safety critical systems, we can utilize this entropy score in order for the decision making module in conversational agent to take a safe decision. Or we could, for example, we can have a fault tolerance mechanism or a separate monitor with this architecture, that if the understanding is very uncertain, because the decision making will just follow what the understanding module has learned in conversation agent, so the decision could be very wrong, and in healthcare it could be catastrophic. The evaluation dataset, as I mentioned earlier, contained 1000 examples, and the results were very good. So one limitation could be that we should try to add more test data. 1000 examples maybe not enough, but in comparison to the training and testing dataset, this size seems reasonable. So for future work, we want to apply the robust technique in NLU models for conversational agents, where the conversational agent is performing multiple tasks of intent classification and slot filling. So the model will be models that provide joint intent classification and slot filling tasks. We want to detect any incorrect user input that has not been seen by our model during the training. So that's all from my side. Thanks for listening to my presentation.